Okay, continuing our look at polynomial functions, let's talk about the rational zeros theorem. Now let me give you a sense of what our goal is here. Our goal is to eventually solve polynomial functions. So we're working toward that goal by kind of speaking about the various pieces that are involved in how to solve a polynomial. Okay, so in solving it, of course, means finding the zeros of the polynomial. So our objective for this video lecture, use the rational zeros theorem to list the potential rational zeros of a polynomial. Not a polygon, I got myself confused last time. Polynomial function. I guess I'm still thinking a little bit about geometry. Okay, so what do we know here? Okay, a zero of a polynomial function is a number that solves the equation f of x equals 0. We did a lot of this with quadratics. We set them equal to 0, and we factored, or we used the quadratic formula, or we used the square roots, or various methods to find the zeros, okay? The zeros can be real or they can be imaginary or complex. And again, we saw this with our quadratic functions. We're going to focus on this video lecture, we're going to focus on real roots. In particular, we're going to focus on rational roots. Okay, so a rational zero, I keep writing the word polygon. A rational zero of a polynomial function is a rational number, okay? It's a number that a rational number is a number that can be written as a fraction of two integers. Okay, so 5 is rational, 5 over 1. 1/2 is rational, it's already a fraction. Negative 34 thousandths is a fraction, 34 over 1,000, or negative 34 over 1,000. Okay, so it's a rational number that solves the equation f of x equals 0. Okay, real zeros, which is what we've been talking about, okay, we're going to get more into in the next video lecture. Real zeros include rational zeros because your real numbers include your rational numbers. So real zeros are places where the function's graph touches or crosses the x-axis. These are your x-intercepts. Okay, those are your real zeros. They solve the equation f of x equals 0. They are telling you where does this graph touch or cross the x-axis. So here is the rational zeros theorem. If a polynomial function written in standard form, which means in descending order of exponents, has integer coefficients, so the coefficients are not fractions, they're integers, then any rational zero must be of the form plus or minus p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. That's your rational zeros theorem. So we're going to try to find potential rational zeros. Let's take a look at a couple of examples to do this. Okay, and we'll also make use of our calculator to see that it works. Example 1, list the potential rational zeros of this polynomial function. F of x equals 2x cubed plus 3x squared minus 8x plus 3. We know it's a degree 3. All of our coefficients are integers, and we have written them in descending order. Okay, so p are your factors of 3, which is the constant. Remember from our theorem, p is the factors of the constant. Well, 3 has factors either plus or minus 1, has two factors, plus or minus 1, plus or minus 3. Those are the factors of 3. Again, positive 1 times positive 3 is 3. Negative 1 times negative 3 is 3. So I've covered all the factors of 3. Q is the factors of 2, which is the leading coefficient right here. Okay, factors of 2, plus or minus 1, and plus or minus 2. So our potential rational zeros, okay, the place where this function may cross the x-axis, will be found with plus or minus p over q. Okay, so plus or minus 1 over 1, I wrote here. Plus or minus 1 over 2, I wrote here. And then because I've exhausted the 1, I'll now go to the 3. Plus or minus 3 over 1, I wrote here. And plus or minus 3 over 2, I'll write here. Okay, we can simplify this. 1 over 1 is simply 1. And 3 over 1 is simply 3. So we have 8. Positive 1, negative 1. Positive 1/2, negative 1/2. Positive 3, negative 3. Positive 3/2, negative 3/2. 8 potential places where this polynomial crosses or touches the x-axis, where we have an x-intercept. Out of curiosity, let's take a look at where they actually are. We could use our graph to find that. Okay, y equals, I've cleared out my y equals here, so let's put it in there. 2x cubed plus 3x squared minus 8x plus 3. I'll use my standard window, so just in case, zoom 6 to go to standard. And you can see my function being drawn here. Okay? And you can see, even though it tops out above, this function crosses the x-axis in 3 places. Okay, let's see if they should match up with our potential rational, because these are the potential rational ones. Okay, let's see if any of them match up with our potential rational ones. I'm going to zoom in. I'm going to change my window a little bit and go from -4 to 4. And there we go, up, coming back down, and it crosses. So it looks like this is -3, and here we have a -3 as a potential. I'm betting that this first one here is positive 1/2. Let's do a quick calc of a 0. My bounds above and below in this case. And sure enough, positive 1/2, which is positive 1/2 here. And it looks like that one right there is positive 1. So it turns out that we found all of the rational zeros using this method, our rational zeros theorem. Okay, let's do that again with another example, just to solidify that a little bit. List the potential rational zeros of this function. Again, it's the 3rd degree. 3x cubed plus 8x squared minus 7x minus 12. Okay, so P, again, is the factors of the constant term. The constant term is -12. Well, that's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Those are all factors of -12. Q, again, is the factors of the leading coefficient. Our leading coefficient is 3. So we have plus or minus 1 and plus or minus 3. So our potential rational zeros are plus or minus P over Q, and we have a lot of them. I'll do the same thing. I'll do P until I exhaust it with Q underneath, and then I'll do the second P, the third. So plus or minus 1 over 1, plus or minus 1 over 3. Okay, I've exhausted the 1. Now I'll go to the numerator 2. Plus or minus 2 over 1. Plus or minus 2 over 3. Okay, now let's go to the 3. Plus or minus 3 over, 3 over 1. Plus or minus 3 over 3. Plus or minus 4 over 1, plus or minus 4 over 4, plus or minus 6 over 1, plus or minus 6 over 6, plus or minus 12 over, oops, made a mistake. This is 4 over 3. Look at me. 1, 3, 1, 3, 1, 3, 1, 3. I bet you're thinking, what is he doing? Okay, 1, 3, 1, 3, and then I knew it didn't make sense when I put 12 over 12, plus or minus 12 over 3. Okay, so I 1 over 1, 1 over 3, 2 over 1, 2 over 3, 3 over 1, 3 over 3, 4 over 1, 4 over 3, 6, and 12. I have them all. Let's simplify this. This is plus or minus 1. This is plus or minus 1/3. This is plus or minus 2. This is plus or minus 2/3. This is plus or minus 3. This is plus or minus 1. This is plus or minus 4. This is plus or minus 4/3. This is plus or minus 6. This is plus or minus 2. This is plus or minus 12, and this is plus or minus 4. I don't need the repeats, so let's see here. I got a second positive negative 1. I got a second positive negative 2, and I have a second positive or negative 4. So the potential rational zeros, positive or negative 1, positive or negative 1/3, positive or negative 2, positive or negative 2/3, positive or negative 3, positive or negative 4, positive or negative 4/3, positive or negative 6, and positive or negative 12. 2, 4, 6, 8, 10, 12, 14. There are 18 potential rational zeros. Okay? Out of curiosity again, let's take a look and see what our calculator tells us. If any of them, we should have some of them. Whoops, I gotta get my light out of the way here. Let's go up to there, that's better. Okay, I'm trying to get the light off the screen for you, okay? So let's see here. Let's go back to my y equals. And now I have 3x cubed plus 8x squared minus 7x minus 12. I'll go back to the standard window just to start myself off and see where things work out. Okay, it looks like I've got 3, and I can probably do a little bit of, I can probably zoom in closer on the x-axis. So let's go from -5 to 5 again. Whoops. And it looks like, well, that's one at -2. Oh, excuse me, that's at -3. That looks to be at -1, and this looks to be at maybe 1 1/3 or positive 4/3, which I see right here. Let's just check that. Calc the 0. Okay, let's go over to that one. I want to be on the opposite sides of that place. And sure enough, 1.3 repeating is the same as 4/3. So again, in this case, it gave me all the zeros because all the zeros are rational. So I came up with all of them. All right, so we're moving towards solving polynomials. Next up, we're going to find the real zeros. Okay, rational zeros, real numbers include your square roots, pi's, square root of 2, the number e, but primarily the square roots. So we're going to look at how to find the real zeros in our next video lecture.